Okay, dear students, welcome back to solving again numerical problems from engineering mechanics. McGraw-Hill publication, 5th edition, written by Professor Timoshenko, Professor D.H. Young of Stanford University, Director J.V. Rao, Professor Sukumar Pati. Now, I'll be solving one problem from problem set 2.6, solution to 2.96. So, a simple one. Well, you can look at the diagram figure. A prismatic bar, AB is a prismatic bar. It has a weight Q from the center of mass acting vertically downward. Prismatic means all throughout the cross section is same. A prismatic bar AB of weight Q and length L. From here to here, the length of the prismatic bar. This is hinged at A and supported at point B by an elastic spring. The point B is connected by a spring which passes over a pulley. The spring is fixed at the other end D here as shown in the figure. The distance between the hinge at A and the pulley from here to here is also L, means same thing as the length of the prismatic bar. Of the bar AB. The stiffness of the spring is K, means the force constant, and the spring is unstretched when the bar AB is horizontal. When AB was in this position, when AB bar was in this position, the spring was not stretched. All right. Find the configuration of equilibrium of the system as defined by the angle alpha, this angle alpha, which the bar makes with the horizontal as shown in the figure in terms of the weight Q, the spring constant K, and the length of the prismatic bar L. Now, let me slightly explain you. When this prismatic bar, the end B connected to the spring, which passes over a pulley and fixed here, when the prismatic bar was horizontal like this, the spring was in a unstretched condition. Now, then why the new position is like this? Because due to the weight Q, the line of action of Q, if you from this point has a perpendicular distance. The line of action of Q from this end has a perpendicular distance, this perpendicular distance. So the Q will produce a turning effect about point A. So the prismatic bar is in now this position, making this angle alpha. So the spring is stretched. Let us consider the C a point to be here, right? So let me now read out and explain also. So Q is the weight of the bar. Line of action of Q has a perpendicular distance from A, so it produces a turning effect that is anti-clockwise. So the spring is stretched. Now, well, you can imagine when the prismatic bar is in this position, the horizontal position, in this position, then alpha is 0. When alpha is 0, the spring is not stretched. When alpha is 0, the spring was not stretched. Now, as you know, when you stretch a spring, the spring applies a restoring force in the opposite direction, tries to regain its original configuration. That force is called the restoring force. Let it be F. Let it be F. Right. Now let the stretch from C to B produced in the spring is equal to X. So, as you know, the restoring force F is proportional to X. Rather, F is proportional to negative of X. So, F is equal to minus Kx. The negative sign only indicates the restoring force F and the stretch. They are opposite to each other. And K is your spring constant, or called the stiffness of the string. So, when X is 0, there is no stretch produced in the spring. then 0 into k is 0, so F is 0. So F is 0. So sorry, the video got slightly less visible because the light went off. I am resuming again. So clear about how F is equal to 0 when x is 0. And when x is 0, there is no stretch. When the spring has not been stretched, that is x is equal to 0, then alpha is also 0. So alpha is also 0. So what is to be imagined here, this angle ABC is not 90 degree here. This is what you have to be careful. If you get a right angle triangle only, then we can apply sine theta, cos theta, and find out different values. So this part of the diagram is redrawn here. I have redrawn it. As you can see. A is the prismatic bar. AC was the horizontal position. It has been tilted by angle alpha. So from point A, if I draw a perpendicular on CB or BC, which is the stretch, which is equal to x, then from C to E will be equal to from E to B will be x by 2 each, since CB is equal to x, the stretch produced in the spring. So CE will be equal to EB will be x by 2, and this angle CAB, which was earlier alpha, now is divided into two equal angles, alpha by 2 and alpha by 2, because this is the perpendicular bisector, right? So either in this triangle or in this triangle, if you take sine alpha by 2 will be BE over EB over the hypotenuse L. So cross multiplying your EB, which is same thing as CE, will be L times sine alpha by 2. So therefore the stretch from C to B produced in the spring when the prismatic bar is in this position, the stretch from C to B, that is equal to x, which I have taken as x, will be equal to 2 times this, 2 sine alpha by 2. Now, since F is equal to minus kx, the spring force, the negative sign only means F and x are opposite to each other. So, put the value of x here. So, your spring force becomes k times 2L sine alpha by 2. This value of x here. Now, let us go to the next page. Now, once that is done, now a few more minutes. Now we have to find out which forces will be producing a turning effect about the point A. The figure is again redrawn. Let me show you once more here. This is alpha by 2, this is 90. So in this triangle, the remaining angle will be 90 minus alpha by 2. So now the diagram is again redrawn. This is the point where the prismatic bar was hinged. The prismatic bar from its horizontal position has been shifted down due to its weight Q, and the line of action of Q, when produced to this side, the line of action of Q from the point A has this perpendicular distance from A to F. This angle is 90. From A to E will be half of the length AB. That is, from A to E will be L by 2. So to find out this perpendicular distance, if I take cos of alpha in this triangle and cos multiply, I will get AF. And the spring force I have shown at point B. The spring force I have shown at means when the bar is tilted, this is the direction of the spring force. Now trying to regain its original shape. So the spring force I have shown it here, making angle 90 minus alpha by 2. And this spring force F is resolved into two components. one along this and one along this, such that, so this one becomes f of cos 90 minus alpha by 2, and this force passes the line of action of this force, a component of the spring force. The line of action of this force passes through the point A, means this does not have a perpendicular distance from point A, so this will not produce a turning effect about point A. Whereas this one, f of sine 90 minus alpha by 2, is at this perpendicular distance from A to B. This has a perpendicular distance from A, and that perpendicular distance is from A to B, that is the length of the prismatic bar. So that is what I have explained here. Now let us apply some of the moments about point A. Since it is in equilibrium, the clockwise turning effect, the anti-clockwise turning effect will be equal and opposite. So f of sine 90 minus alpha by 2 times L, which will produce a clockwise torque, is equal to q times the perpendicular distance AF. Q times the perpendicular distance AF. Now in triangle AFE, if you take cosine alpha, in this triangle cos of alpha will be AF over AE, AF over AE, AF. AE is half of the length of the prismatic bar, so you get AF is equal to L over 2 cos alpha. Now put this value of AF here and let us rewrite the equation. This equation, f of sine 90 minus alpha by 2 times ABL is equal to q times the value of AF, L by 2 cos alpha. Now put the value of F, the spring force, which we calculated in the previous page here, spring force, K times 2L sine alpha by 2. So put the value of F, sine 90 minus alpha by 2 times L q L by 2 cos alpha. Now I will keep 2 with this term, and sine 90 minus alpha by 2 will be cos alpha by 2. So I will be getting a new trigonometric expression to remove alpha by 2. So K times 2L sine alpha by 2 cos alpha by 2, that is this sine 90 minus alpha by 2 is cos alpha by 2, L is this much. Now keep this 2 along with this and with this in a bracket, and KL remains same. So this comes under a trigonometric formula, sine of 2 theta. 2 sine theta cos theta, that is sine of 2 theta, sine of 2 alpha by 2, 2 cancels. So 2 cancels. So we are left with KL sine alpha times L q times L by 2 cos alpha. Now, so bring cos alpha here, it becomes sine alpha over cos alpha tan alpha, q L over 2, q L over 2. Bring this scale here and this L here. So now LL cancels. So q over 2KL. Q over 2KL is your tangent of alpha. So tan alpha is q over 2KL. So alpha is tan inverse q over 2KL. It's an interesting one. It's not very difficult. I hope you liked it. And if you find the videos are comfortable for you and is really helping you, you may subscribe and pass on to your friends also. All the best. Thank you.